Okay, okay. Hello to you all. We're back to the final session of this symposium, and in this occasion we have a pre-recorded talk from Dr. Nelson Flores Gallegos from Centro Universitario de los Valles, Universidad de Guadalajara, and the name of this talk is some generalities of the applications of information theory in chemistry. So I'm going to play. Okay.
I'd like to start this presentation with the following question about the application of some aspects of the information theory to the chemistry. In this case, I would like to start with the following question and why we use the information theory to describe in order to describe chemical systems. In this case, we have to represent in the most general form two subsystems. In this case, we have the subsystem A and subsystem B that we can share some kind of information. For example, if we think about a T-shirt, we can form groups that some characteristics of these T-shirts can share. For example, the number of buttons, the color, or something like that. In this sense, we have that the subsystems A and B, we can share some kind of information that they characteristic of them. In this sense, we can express these general diagrams in terms of probability. In this case, we have the probability of the joint probability, the probability of the subsystem A, the mutual probability, and the conditional probability. In this case, we can form or write some expression of entropy because one of the main ingredients of these definitions is the probability. In this context, we can express this a bunch of probability or expressions of Shannon's entropy, which is perhaps one of the most known or well-known concepts of the information theory. In general, we have that we can use these two expressions of the entropy. One of them defined in terms of the electron density in position space and in momentum, the electron density in momentum space. However, we have to be careful with these expressions, and this is because these both equations have with the main characteristics the use of the presence of the logarithm. In this case, we can express several expressions of entropy in position and momentum space. But we have also we have that we can do a link with the information theory and quantum chemistry through the electron densities and density matrix. This permits us to study the theory of atoms and molecules and chemical reactivity theory. However, as we mentioned before, we need to be careful with these expressions, and this is as follows. In this case, we observe that the natural logarithm is a transcendental function So, as we mentioned before, the natural logarithm is a transcendental function, and in this case, such kind of functions can has units in their arguments. So if we do a dimension analysis, we observe that the argument of the natural logarithm is has units of number particles by element of volume. So with this a mistake in this case, and the other common expression for Shannon entropy is defined in terms of the shape factor, which is defined like the electron density by electron number. Okay, so if we again perform a dimension analysis, we observe that in this case the natural logarithm has its argument has units, which again is a mistake. In this sense, if we perform a revision of the electron density distribution, we observe that at the nucleus position, for example, we have that we find the maximum value of the electron density. And in this case, we observe the presence of two zones. In this case, when the electron density take values greater than the unit, we observe that, or we obtain as a result that the entropy will be negative. So which is a clear violation of the one of the main properties of entropy. In this sense, if we observe the values, we know that in some point the electron density will take the value of the unit, and therefore we obtain at this point that the entropy will be zero. So in the sum number 2, we observe that the values of the electron density are minor than the unit, and therefore the entropy will be positive. Therefore, we have that the Shannon entropy defined in terms of the electron density or in terms of the shape factor, the numerical values will be negative, positive, or even equal to zero. So in this case, we have some proposals, and one of them is define the electron density divided by the maximum value of the electron density. In this case, we observe that this argument will be dimensionless, and in this case, the shape factor multiplied by this volume element will produce a dimensionless definition. So the other expression that we propose recently is the divide or renormalize the electron density by rho max in the following way, such that we obtain that the following expression. In this case, we observe that this equation will be completely dimensionless, and we follow without the characteristics of the entropy. So let me to please present this aspect. In this case, I show you the density, the radial distribution profile of the argon. In this case, we observe that the Shannon entropy defined in terms of the electron density, there is a zone in which the values are negative. In this case, a ring, we can figure out this like a onion in which in the kernel the entropy will be negative, which of course that don't has any physical sense. So if we analyze the same profile but considering the Shannon entropy defined in terms of the J factor, we observe the same situation. There is a zone in which the Shannon entropy is negative. There is a point in which this expression is 0, and there is a zone in which is positive. So if we consider, if we consider the atoms of the periodical table, we observe that how the question here is how can we know which expression is the correct. So in this case, if we analyze, we check, for example, the general trends of the Shannon entropy defined in terms of the electron density, we observe a decreasing behavior. We don't know if it's correct. So in the case of the Shannon entropy defined in terms of the J factor, we observe the same situation. However, in the early 90s, Collins proposed that the electron correlation there is a relationship between electron correlation and the positive form of the Shannon entropy. In this case, if we observe that, we expect that for any atoms, if we increase the electron number, we expect that the electron correlations will be greater and more important. However, in these both expressions, we observe that physically maybe the interactions electron-electron decrease. So, which is a contradiction to the physical or chemical sense in this case. However, when we use the Shannon entropy in the correct form, that is defined in terms of electron probability distribution, and we obtain that the general trends are increased according to the electron number. So there is there are some other concepts of the information theory that are virtually not explored. In this case, for example, we have the information energy, which is defined in this way. So if we have the informational energy, and we have the information entropy, of course we can define the information temperature in this case. So there is another very, very interesting concept, which is the redundance. In this case, this redundance can be used as a measure of electron correlation measure. So we have other concepts of the information theory that, like the information channels, the information balance, and some other concepts that are, I insist, virtually not explored into the field of the chemistry in this sense. Now, there is another field of the information theory in which one of the main characteristics is the generalized entropies. In this case, perhaps the most famous definition of entropy is solid entropy. In this case, one of the aspects or the problems of the solid entropy is that this expression depends on Q parameter, and we don't know what it is. So, but if we recur to the probability theory, we have the Levy distributions, and these Levy distributions, which are probability distribution related to some physical aspects of but the main characteristic is that those Levy distributions depends on this Q parameter. And observe that in this case we have 1 by 3, 2 by 3, 4 by 3, 5 by 3. In this case, if we take 4 by 3 and 5 by 3 and we plug in this equation, we obtain exactly the same form that the local functionals. In this case, for example, if we use 4 by 3, we obtain the exchange functional. 5 by 3, we obtain the Fermi-Dirac kinetic energy functional, and the electron-electron repulsion functional. So a good hypothesis is express the electron energy like a sum of entropies, which ties perfectly with the Collins conjecture. In this case, well, we performed some work and we could write this expression. So in this case, this functional, which is a sum of entropies, we of course compare with the well-known methodology, which such as Hartree-Fock, and in our results are the black points, and the Hartree-Fock numerical results are the red ones. So we observe that when we increase the electron numbers, we fail to predict the correct values of the electron energy. Of course, we can plug some proportional, some constant that permit us rewrite this functional in order to get most or adequate values. So there is another aspect that is very interesting, I think. So there is the relationship between Shannon entropy and the theoretical chemical reactivity descriptors. In this case, for example, if we take the first derivative of the Shannon entropy respect to the electron numbers, we obtain that this part of the integral, we recognize that this is the Foucault function. So this is in respect to the continuous Shannon entropy. However, we can define, we can try to figure out if there is a possible relationship between discrete Shannon entropy and some descriptors of the chemical reactivity. In this case, for example, if we consider the neutral chemical species, anion and cation, we consider the first their corresponding occupation numbers, we can perform the following operation. In this case, for example, if we performs the following expression, we have the difference between these two population analysis, and if we consider a general form of this distribution, we can take the power of k of each term, and if we take the first derivative or respect to this parameter k, we obtain the exactly, and consider k equal to 1, we observe that the slope of this figure can be related to the electron affinity and the first ionization potential. So if we have these two important concepts of the chemistry linked to the change of the entropy of the systems, of course we can relate this to the hardness. In this In this case, if we consider, for example, the following expression of the hardness, in this case we use a set of molecules of a large set of molecules, we observe that or equation of the change of the Shannon entropy is related. We can reproduce the distribution of the hardness using the traditional concepts. On the other hand, we have that in chemistry we can observe the application of several definitions of entropies, and of course we have one of them is Range's entropy, Fisher entropy, Shannon entropy. This one that is virtually not explored into the field of chemistry, the trigonometric entropy, Zalt's entropy, von Neumann entropy. Anyway, and also we recently proposed some new expression of entropy. In this case, Shannon-Jackson entropy, which is this one, and Range-Jackson, entropy, which is this one. And of course, we have also some other concepts. In this case, we have the Kullback-Leibler divergence, Fermi-Dirac's entropy, Q-Range's entropy, Range's divergence, and so on. So there is some applications. Let me show you some of them. And this is in the case of the Hammond postulate. In this case, one of the main problems in order to study some chemical reactions is try to figure out which could be the possible structure of the transition state. In this case, we recur in general to the Hammond postulate. In this case, according to this postulate, the transition state structure will be more similar to the reactants, and in this case, in the exothermic reaction, we have that the transition state structure will be more similar to the products. However, let me show you some results using the Kullback-Leibler divergence. So in this case, we have that if the numerical result of this equation is more closer to zero, then both distributions will be more similar. So in this case, we present this exothermic reaction, and according to Hammond, we have that the reactants structure will be more similar to the transition state. And in the case of the Kullback-Leibler divergence, we observe exactly the same result. So however, in this case, we have an endothermic reaction, and we know that according to Hammond, the transition state structure will be more similar to the products. However, in this case, we observe that there is some other structures that are more similar to the transition state. In this case, at this point. So it is, I consider remarkable to note that this expression of the Kullback-Leibler divergence permits us to compare some things, two different things. In this case, for example, the structure of the transition states. However, we can extend this idea to the comparison. In this case, we have the chemical similarity idea, which is how to find some molecules that could share some chemical or physical characteristics. In this case, we recur to the Range divergence, and we select in a random way in a large set of molecules. We select one of them and we compare with all our set. And we found that we did in this case, these 5 molecules have some characteristics that very interesting. So In this case, we observe that these two molecules, their chemical potential are very similar. Okay, so there is another concepts of the information theory. In this case, we have those rangy entropies that we can define in terms of two or more subsystems, and in this case, we have the following expressions. Okay, so in recent work, we are studying some chemical reactions using these expressions of ranges entropy, and in this case, we observe, for example, that the energy profile in this case the trends in red color, it doesn't say any too much so about this chemical reaction. However, when we compare with the Shannon entropy, in this case is the discrete Shannon entropy, we observe that this trend presents more complex structure. And let me show you this slide. In this case, we observe that, for example, at the transition state, we can observe how this process is carried out. So in this case, this maximum and minimum could be related to the bond breaking and bond forming of these molecules. Of course, as we mentioned before, we can define or study these chemical reactions, or in general any chemical reaction, using this idea of two subsystems that can interact. So in this case, we choose system A and system B, and we analyze this aspect of this chemical reaction, and we observe that the general trends are more complex and sophisticated. That, however, it's clear that the maximum minimum that we observe in these chemical reactions in this profile of the ranges entropy are related to the process of the bond forming and bond breaking of these systems, and we can perform a lot of analysis using these ideas, which permit us to analyze these chemical reactions in a different way, or maybe perhaps using a different perspective of this process beyond of the classical energy profile, or the energy, the electron correlation energy profile, and something like that. So, in general, we I could say that these concepts of the information theory are a very useful or powerful concepts and tools that permit us to study the chemical systems in a more general way. And of course, these concepts are related to the chemical reactivity, chemical similarity, electron correlation, and among others. Thank you very much for your attention.
Okay. We thank Dr. Nelson for his interesting talk. And well, we have another talk in a few minutes. Okay, our next talk is starting 4:35, so we have a little break of 5 minutes. Thank you for your attention.
Sí, sí. ¿Ya está? Ah, ok. Ok. Entonces, pero tú lo vas a ver si están escuchando, Roberto. Ah, ok. Ok. Sí, sí, yo pregunto, ¿no? Sí, sí. Si quieres. Ok. Ok. Can you hear me? Can you hear me? Can you hear me?
We can hear you very
Yeah.
well.
Oh, thank you. Thank you.
Okay, we are back again, and this is our last talk of the day and the symposium. And we have the honor to have one of the main professors here in UAM in chemistry, the Professor Robin Sagar. And in this occasion, he will talk us about uncertainties and statistical correlations in quantum systems. And the microphone is yours, Professor Robin.
Thank you very much, Ernesto. So the title of my talk today is Uncertainties and Statistical Correlations in Quantum Systems. So if you could please go to the next slide. The outline of my talk is I'd like to give some historical perspectives on why we do this kind of work. I'm a quantum chemist, so I would like to just to speak briefly about what were the motivations at the beginning. Then I'll go on to speak about uncertainties and the relation with information entropies. And the basis of this HUP is the Heisenberg uncertainty principle. After that, I'd like to go on to speak about statistical correlations and how uncertainties are related with this statistical correlations. And then finally, I'd like to just speak a little bit about future challenges and what we have planned or what open it up to the community to see what we can achieve in the future. Okay, so please next slide. Yeah, so in the historical context, I think this paper in 1985 is, I can't say that it's the first, but I think it's one of the first. And I think in an earlier talk, Paul was talking about he first met Sears when he was 5. And I think this paper, I think Gaudry is the first author, but Sears was definitely played a big role in this paper. And in this paper, it was a study of, among other model systems, neutral atoms. And what they did was they studied neutral atoms in the periodic table, and they studied entropies in position and also momentum space. Okay, so now, why the interest in Shannon entropies why the interest in Shannon entropies at this point? So I'm taking you back in time. I'm trying to explain what are the motivations. I was reminiscing with Rodolfo recently, and for a long time when people entered into this, they couldn't really understand, understand why somebody would be interested in studying information entropries, okay? So why the interest in Shannon entropries? Well, one, because they're defined in terms of densities. I'm gonna define the entropries a little bit later on in terms of the densities. And why the interest in densities? Well, because they're experimentally accessible. We now know that crystallography has evolved to quantum crystallography that has been recently introduced. Secondly, if you're speaking about a density, very related to density functional theory and the development of density functional theory, quantum theory of atoms and molecules at this time was coming into its own. And also, most importantly, is that in this paper of Gaudry and Sears and others, they explored both entropies in position, but also in momentum space. And one of the things that we were interested in at this time was the development in momentum space, because what was going on this time in the 70s and the 80s, there was an impetus about building a momentum space quantum chemistry. So equally studying position space, studying momentum space, studying entropies, this was the basis of why the interest. And of course, I just briefly mentioned that momentum densities there are experiments, E2E spectroscopy. So these are experimentally accessible things, okay? So please, Ernesto, the next one. So now, what are the relations between entropies and physical concepts? At this time, the entropy, now we saw earlier on some beautiful work where people are just applying entropies and they're getting to know, or they're examining what is happening to the system. But back, we're speaking in the 80s, in the late 80s, it wasn't that well defined. So we were trying to understand what are the relations between entropies and physical concepts. Now, and in that paper that I mentioned in the previous slide, in the Gaudry-Sears paper, they proposed that the entropy sum is a measure of wave function quality. And as in quantum chemistry, we all know that most of our functions, well, if not, well, all of it minus one, we're not speaking about analytical solutions. We need approximations. So in quantum chemistry, it's very, very important to understand how good is your approximation. So if the entropy sum could be a measure of wave function quality, that was indeed very, very interesting, okay? Secondly, Kalidas mentioned this earlier in his work, stopping power measurements. Now, in the local plasma approximation, which is due, I think, to Linhart, you have something that's called the mean excitation energy, and this is directly related to the Shannon entropy. So it gives you a physical basis to understand what is entropy. What is entropy, okay? Other proposals, the entropy sum is a measure of correlation in atomic systems, okay? Also, very briefly, Rodolfo mentioned this in his talk. Shihai, I think, actually shows some calculations where you can use Nelson, just a while ago. You can use a discrete form of Shannon entropy where you're using the eigenvalues of the one matrix, and this could be related to the correlation energy, okay? Now, this correlation energy, right, it's the difference between the exact non-relativistic energy and the Hartree-Fock energy, and it's something that was introduced in quantum chemistry to try to give us an idea of how good the approximate wave function is. Go ahead, I just ask you to remember that definition because I'd like to come back to it when we're speaking about things later on, okay? So this is just about what was happening at this time. Please, Ernesto. So now, uncertainty relations, okay? And what is the role of entropies in these uncertainty relations? Well, we have first the Heisenberg uncertainty relation. I found it very, very interesting in Vlatko's talk. What he said was that Heisenberg uncertainty principle is at the heart of quantum mechanics. You cannot get away from it. Now, what I have in the first box here is the formulation, which is due to Kennard-Robertson, and this is the formulation in terms of standard deviations. Now, standard deviations, there are some, what you're doing is that you're using standard deviations, but in a sense, you are implying that your distributions are normal or Gaussian. Now, we know in quantum mechanics that doesn't happen for a lot of systems, especially when we're speaking about atomic molecular systems. So Kenneth Robertson produced this, and what has been happening lately is that there is a migration of people leaving behind the definition or the formulation of HUP, the Heisenberg uncertainty principle, in terms of the standard deviations, and they're migrating to entropic forms. And I just have some of the references here. There's a later work that was published in 2019. Okay. So now entropies and the sum of the entropies, the x position, p momentum space. It's a formulation of the uncertainty relation. Okay, please. Okay, now uncertainty measures. Now, Shannon entropy in quantum mechanics, these are the position space Shannon entropy on the left, and on the right, the momentum space Shannon entropy. It's defined now in terms of wave functions, okay? So what I'm doing here is that I'm trying, in a very indirect manner, I'm trying to escape something that what I'd really like to stress is that these are okay for in chemical systems if you're speaking about one electron problems. But when you go to 2 electrons or more, what you have to use to use these are the reduced densities. Okay, you're using reduced densities. Okay, so you're not using the definitions in terms of the wave functions. Okay, so that is something that I'd like to point out. Now, why in this? You have the Schrodinger equation. We have the wave function that we get from the Schrodinger equation, right? The Born interpretation is that it's a probability distribution. So now you apply these the definitions of the Shannon entropies to these densities, and what you get is a measure of uncertainty. And we've seen this throughout the meeting. The 4 days that we've had, a lot of it has been discussed, and just very, very briefly, because everybody, or most people who've spoken, they said it, right? When the entropy goes down, we're speaking about a decreased uncertainty, and when it increases, we're speaking about an increased uncertainty. So, right? Another way of saying increased uncertainty is delocalization, and the reverse is localization. Now, in chemical terms, every chemist knows that there are a lot of processes that chemists are very interested in when delocalization occurs. So if you have a measure that can measure the extent of delocalization, it's very interesting from a chemical point of view. Just something that I should say, the definitions that we're using, usually people say, well, they're not really Shannon entropies, they're differential entropies because we're applying these definitions to continuous distributions. So our distributions that we're interested in are continuous variable quantum systems, okay? So please, Ernesto, please. Okay, so now, just to give you an idea, and I mean, we've seen this during the whole, in the meeting. Shannon entropy isn't the only measure of uncertainty. There are Rényi measures. I think Agnes spoke about this. I think Elvira también also spoke about this. And it collapses because what you have in the Rényi entropy is that you have a parameter. So you have an extra degree of freedom, and it's very interesting to see, okay, what physical information does the parameter have for what your physical system? And when this parameter goes to 1, you recover the Shannon entropy. And also we have the Salis entropy. Nelson, a couple of minutes ago, was speaking about the Salis entropy. Now, these things can be combined. These are the basis that you can form complexity measures. You know, that's another story. I won't go in. There's a lot of work that has been done. Juan Carlos was in the group in Granada. Colleagues, Rodolfo has collaborated with them to study complexity measures. We saw a very nice talk yesterday, I believe. Angel Plastino gave us a nice talk. Kalidas was talking about the complexity measures. So that's another route you can go. Also, I would like to say that there are uncertainty relations in terms of Rényi entropies also. I think maybe Agnes and also Elvira, they spoke about defining the uncertainty relations in terms of the Rényi entropy. So Shannon entropy is just one branch, but I think the core of what we're trying to think about are uncertainty relationships, the Heisenberg uncertainty relations. Please, Ernesto, please. Now, open questions. What is the appropriate measure to capture quantum uncertainties? 2, what do the quantum uncertainties tell us about the system? And just, I had an idea while I was sitting, and I was the moderator earlier on, and I was watching. I was fortunate enough to be the moderator for the confined system, we would call it the confined system community. Well, not really, because I think Jayanta, yesterday, he started it off speaking about, I think he was the first speaking about the confined systems. So what you're seeing is that these measures are being used as a tool to understand what happens to the system when something changes. Vinod was speaking to us earlier about what happens when you apply an electric field. And you can apply these measures to understand what is happening to the density, as parameters of the system changes, as they change, okay? So the idea is that, well, information is encoded in the wave function, or I would have to say, if you're speaking about, say, maybe one particle problems, or if you're not, you're speaking about with more particles, you are reducing the density coming down into the one particle or one variable. Okay, so you're trying to see how is this information encoded. And the big question is, if the information is in there, how to extract that? And one can argue, well, that is what information theory is. You're trying to extract information, okay? Now, I'd like to go on. Uncertainty relations, we're told, well, it's an idea, the uncertainty, and I think why Vlatko was saying, well, the uncertainty principle is at the heart of quantum mechanical behavior, because really quantum mechanical objects are waves. So they're waves, so you have to think about them in this way. So now, if there's a position momentum correlation, how can one go about measuring this position momentum correlation? Ernesto, please. Okay, so now we're going to talk about phase space distributions, because normally we speak about position space, momentum space. I haven't said this here, but you can get over to momentum space by Fourier transforming your position space wave function, okay? But usually, oh well, you do the analysis in position space, you do the analysis in momentum space. Now, the question is, well, can you do it in a joint position momentum representation? And this leads you to the topic of phase space distributions. And like it's what we saw, Elvira was, I think, first to speak about the phase space distributions. I'll have a little bit more to speak about that later on. But we saw Agnes. Agnes was using the phase space distribution from the GBP theory, I think, in density functional theory. You know? So these phase space distributions are interesting quantities, okay? So now, what is the difference? When you go from a density, from a density, you're going to be jumping into a density matrix. And now, these are different ways that you can formulate the problem. The first one is using a phase space Wigner function where the definition of the Wigner function is here, okay? Now, there are problems with the Wigner function because to be able to interpret it as a probability, really people say, well, it's not a probability. And why isn't it a probability? Because there are regions, and for a lot of systems, very many systems, okay, the Wigner function can be negative, okay? So what people say, well, if this is negative, then how can you interpret that as a probability, okay? So this is why people use the word, it's not a probability, it's a quasi-probability, okay? So you know that it normalizes to 1, okay? But it has negative regions, okay? And I think Ernesto is the moderator, Ernesto, and that's the magic about the Wigner function, right? Ernesto was speaking about resource theory in quantum information theory and how people now are trying to use negative parts of the Wigner function in resource theory. Okay, so but that's okay. Okay, well now other possibilities. If you don't like the negative parts of the Wigner function, you say, well, no, right off from the gate, no, I don't want to do this because I don't understand what a negative region of, I don't understand what a negative probability is. There are other options. What you can do is you can use what is called the Husimi function. And the Husimi function here you have in the bottom the definition, and I think formally it's the Weierstrass transform of the Wigner function, and you can think of it as it goes through a smoothing function, and you're smoothing things out, and you're getting rid of these negative regions. No? But there's a price to be paid because the structure inherent in the Wigner function, you're losing it, smearing it out. But what are the advantages? Is you're creating something that's positive, and you don't have the problem of the negative regions. Now, just to give a little more context, or maybe try to put a little bit more emphasis on the Wigner function, there's an active discussion, or it has been, and this has been going on for many years. No, yeah, you can say, well, no, I don't believe in quasi-probabilities. I don't believe in negative. It can't. Distribution functions can't be negative. That's one. Or there are people who say, well, no. These negative regions occur because it's a quantum system. And these negative regions are showing you, it's showing you that you can't try to have a trajectory, as you do in classical mechanics, right, you can't violate Heisenberg uncertainty principle. Okay, so there's a balance there you could take, but I mean, these are the options, right? These are not the only phase-space quantum distributions. There are other in optics that people in quantum optics been uses. There are Glauber, Sudarshan, others with families of distributions. So you can go on, okay? But this is what we want to say. So please, Ernesto, please. Okay, so now what we have here is, and I mean, I don't have a pointer, so I'll have to try to explain what we have, is that the first row is the Wigner function, and this is the harmonic oscillator. And what we have is on the left, we have the ground state, and then in the center and the right, we have excited states. And I think it's the first excited state, and then the second or the third excited state. Okay, and then in the bottom row, what we have is the Husimi function. Okay, so this is just a qualitative. Just try to get what the qualitative features are. Now, in the ground state, which is the left column, okay, you don't see too much difference between the Wigner function above and the Husimi function at the bottom. Okay, but in the excited state, what you do see is that you see a negative region that is being introduced into the Wigner function, and you see the negative region as the negative region is still there in the more highly excited state. Okay, now try to contrast that with what is happening at the bottom. Husimi function, you don't see those negative regions. Okay, but now on the other hand, I'll just invite you to see. Let's take the most highly excited one that's on the right-hand column. And you look at the Wigner function, and you can see the manifestation of the nodal structure in the Wigner function around here. You can see the nodal structure. But then you look down, and you see the corresponding Husimi function, and you see that it's all been averaged over, right? So I mean, there's a loss of detail there. But well, I say I won't go for, well, Wigner or Husimi. I'm just giving what the two distributions are. Okay, so please, Ernesto. Okay, so now, why is the Wigner function attractive? Well, the Wigner function is attractive because the marginals of the Wigner function, that is, you take the Wigner function and you integrate over one of the variables, and what you get is you get the density, okay, in the other representation. So the first one, if you integrate over the mem, what you'll get is the position space density. And if you integrate over the position, you'll get the momentum space density. This doesn't happen for the Husimi functions. if the Yosemite function marginals, okay, are not the position and momentum space densities, okay? So based on this, what you can do now is you can use these distribution functions to define Shannon entropies. So you can define what is the Shannon entropy of a Wigner function and what is the Shannon entropy of the Yosemite function, okay? Now, in the definition of the Yosemite function, I'll just get this a little by, I'll call it by what it's known by in the literature, and that'll be the tie-in to what Elvira presented yesterday, I think, okay? It's positive definite, no negative regions, so there's no problem in applying this definition. On the other hand, you apply the definition you plug in the Wigner function in the definition of the Shannon entropy, and you get something that is a complex valued quantity. Okay, it has an imaginary part to it. Okay, and I'll just give you what the details of that work that was done there. Okay, so now the price to be paid, okay, of defining the Shannon entropy of the Wigner function, okay, is that you don't have something that is real valued now. You have something that is complex valued. Okay? Please, Ernesto, please. Now this is a plot of Wigner and Yosemite Shannon entropies, and the Shannon entropy of the Yosemite function is called the Whirl entropy, and we saw in Elvira's talk, I don't think it was yesterday, I think it was day before yesterday, Elvira presented some very interesting results where in her systems, she was able to use the Whirl entropies, right, the Yosemite function Shannon entropies, to detect quantum phase transitions. So that's something that is very interesting. It really caught my attention, okay? So what we have here, I just ask you to ignore what's going on the right-hand side. No, so it's the left-hand plot. What we have is the red dots. So what we're doing now is that we just try to see how entropies are behaving as a function of quantum number. Very simple model is the harmonic oscillator. Okay, so what you see in the red dots are the Whirl entropies. That's the Yosemite function entropies. Okay, now we have a complex value quantity, which is the Shannon entropy of the Wigner function. So there are two ways. We just took the absolute value, and that's the blue curve, and the green curve is just ignoring the imaginary component and just graphing and just plotting what the real part is. Okay, so what you see in the difference there is, what's nice to say is that all of them seem to increase with quantum number. No, so maybe quantitatively they're not the same, but qualitatively they behave in the same manner. Okay, so and we just have what the article is there. So please, Ernesto. Okay, so now we've spoken about the Shannon entropies of the phase space of the phase space distributions. So now I'd like to just go back. So now, what is the connection? Because remember, we first started with entropy sums. Everybody is interested in entropy sums. We saw the confined quantum system community today. We just saw a lot. We've seen a lot of entropy sums discussions. So entropy sums. So what is the relation between entropy sum and phase space entropies? Well, the entropy sum, you can think about it, it's just the entropy of a separable phase space distribution. Because if you assume that you have a distribution that is the product, it's a product form, okay? So it's separable between rho, the position space density, and the momentum space density, then this simplifies into the entropic sum. So when you are using the entropy sum, what you're doing is that you're using the entropy sum of a separable phase space distribution, the product of the Wigner function marginals. And this in the literature is known as the Leibniz entropy. And for a nice discussion, I just put it here in case anybody is interested in it. It's interesting. So what you do is that if you're using this entropy sum, you're saying, well, yes, sure, you're approximating because you're saying, well, you don't want to go into phase space, okay? And you're using a very particular form of what a phase space distribution is. Now, it's another question whether this is able to capture everything there is, but one can see that it is valid, okay? So please, Ernesto, please. Okay, now I'll speak about the next topic, statistical correlations, okay? Now, statistical correlations, right, we're talking about interactions between particles, quantum and quantum systems, but also the wave function symmetry, okay? Now, this was discussed, I mean, this has a long, long history of statistical correlations in quantum systems. Maybe the first was this paper. I haven't put the reference there, but I mean, it's a very famous paper, Wigner Seitz, in 1930s. But really, it was Kutzelnig and others, right? They were the ones who planted this idea of using statistical correlations, you know, to measure how correlated is your system. Now you'll see this is different. This is a statistical correlation, and this is different from what we were discussing before with the correlation energy. It was studied later on by Thacker and Smith. So what you're doing is that you're applying the correlation coefficient, and what I can see, the difference is that in the correlation energy, you're using the Hartree-Fock energy as a reference. So one can argue is that if you're thinking about a correlated calculation and want to see, well, what's the difference between these two energies? Well, you're changing the system. I mean, it's the Hartree-Fock system that you're using as your reference. One of the characteristics of these statistical correlation measures is that you're not changing the reference, because what you're doing is that this is an expectation value of a pair density, and you're comparing, okay, the marginals of the same pair density with the pair density. So you're not changing the references. It's the same system that you're treating. Now, and this ties in with, I think it was very interesting, and it was in the first day, Christian was talking about this, and he was saying that one should go back to really try to identify what is happening, or what does one mean when you talk about electron correlation. Because people have introduced static correlation, dynamic correlation, but tried to put it on a firmer footing. And this was what he was proposing. And what we can say about statistical correlation, sure, okay, well, what does it measure? What would a statistical correlation measure? Well, it's got everything in there. Okay, you're not separating it. You've got everything in there. You've got the correlation that's due to the wave function symmetry in there. So whether or that is good, that is debatable, but at least it is put on the table. Maybe there's some way that you can think in the same way of what has been done with the correlation energy to try to separate out the components, or maybe it's a better way just to think about, well, that's what is the correlation in the system. I leave that up to you to discuss. Okay, so please, Ernesto. Okay, so now mutual information. Okay, well, we'll speak about this now. In DFT, the focus has been on the one particle reduced density, okay? But, so, and this is reduced if you're speaking about an n particle system, okay? Now, but I just recently said, well, in the definition of the correlation coefficient, you need the pair density, okay? So now, you can get the pair density from if you have a two particle system, or if you have a three particle or more system, you're going to have to reduce to get down to what is a pair density, okay? But you need the pair density, okay, in order to construct these statistical correlation measures, okay? And this is a definition of the mutual information. I won't go much into this because I really enjoyed Peter's talk, which was, I think it was on Tuesday or Wednesday, and then Saul's talk, they spoke very, very, very nicely describing what are the properties of mutual information, okay? Now, this is the definition, okay? So what you see is, and this is a tie-in between uncertainties and correlation, because you can calculate what the statistical correlation is, knowing, okay, what the entropy of a pair density is and what the entropies of the one variable systems are. I just put it here. I just want to make one point. I just put it like this to be in a more general form. But for people working with quantum systems, one of the properties of the wave functions and densities is that they're indistinguishable. So these two one variable Shannon entropies would be equal because they're the same. So what you would have here is twice this minus the pair. Now, and I'll get to later on. I hope I'll get to speak a little bit about the pair entropies and speak about what has been done. And if Juan Carlos is there, we have a good discussion. Okay, see. So now, and what Peter said, what Peter tried to stress, what Saul tried to stress is that mutual information is a more general, nonlinear measure of correlation. Okay, people have been, and it's not just in quantum chemistry or whatever. It's just exploding where people are using mutual information, and they can really see. And I think Peter had some very nice diagrams just showing how you can conceive that mutual information is more general than the correlation coefficient. Okay, please. Okay, so that's the idea between uncertainty and correlation. Now, at this point, we're interested in quantum systems and we're interested in behavior of quantum systems, but just maybe it's nice just to take a step back, and we're thinking, okay, we're interested in uncertainties and we're interested in correlations. And then you can think, well, what other communities have we heard this in? Where are they interested in uncertainties and where are they interested in uncertainty? And we've got what the answer is, data science. Now, so what we can see, what I hope what will happen in the future is that communities will start to collide, people will start to interact among one another, and we're going to see some real developments going on in how you measure uncertainties, how you measure correlations. Okay? So, we've spoken about, and so mutual information we said that we need this pair density, okay? The pair density in position space or the pair density in momentum space, okay? And now, once we have the pair density, we can calculate the mutual information. But also what we can do is that we can calculate a mutual information between X, position, and momentum. And we can do it in this. So remember the definitions that we had for the entropies of the phase space distribution of Wigner and Husimi. Well, we can do the same thing here. Now, what happens is that if you use the Wigner function, and sure, you have to remember that SW there is going to be complex valued because if it has negative regions. But the beauty of it, something I forgot to mention, is that tying in with what Ernesto presented us, people are very interested in negative regions of the Wigner function. Now, it just so happens when one calculates the entropy, okay, the Shannon entropy of the Wigner function, okay, the volume of the negative region, okay, is proportional to the imaginary part of the Wigner function. That's just something to take into consideration, okay? So in terms of, if you define this mutual information in terms of the Wigner function, what you get is the difference between the Wigner function Shannon entropy and the entropy sum, okay? If you do that for the Husimi function, Okay, because the Husimi function marginals are not position momentum space density, you get a sum which is not as above in the Wigner function minus the Husimi Shannon entropy or the Weyl entropy. Okay, Ernesto, please. So these are just some. I just asked you to ignore the center and the right. Just focus on the left. On the left. So we have some plots of this mutual information for the Husimi function, which is given in red. Okay, and again, absolute value and green of and I think that there's an error here because it's not we're not the color code is okay, but we're not looking at entropes, we're looking at mutual informations here, right? Statistical correlations. But what you can see once again is that there's a qualitative they behave in a qualitative manner, right? See, right? They increase, okay? See? That's one thing. Elvira's talk was very interesting when she calculated in these quantum phase transitions, when she calculated the entropies, and maybe just, well, if she sees this, and interesting, and I think she could calculate this, it would be interesting to calculate these these mutual informations, okay, and just see what happens along the quantum phase transition. If she sees this, maybe she, okay? So please, Ernesto, please. Okay, now applications, I mean, you know, it was just fascinating. I mean, I was just thrilled. These 4 days, I mean, it's been joy, just seeing what everything has been done. So applications, I mean, Bernoulli, early on, she's speaking about Bose-Einstein condensations, how you can use this to examine Bose, you know. So what I'd like to, because I got selected on this day, and this is the day of the confined system community. So just like some of the applications that you have for this are in confined quantum systems, okay? So how are we using this? Physical confinement. We heard a lot of work, hard confinement, soft confinement. In confinement, Vinod was talking about confinement when you apply fields, right? So what are the questions? What are people trying to do, okay? How does the system react to confinement? This is what I was speaking about. Use entropies, okay? Is it system localizing? Is it delocalizing? You can use entropies. And Shannon entropy, Rényi, Salis, okay? But bigger question, can entropies be used to tailor quantum control? I'm asking, I don't know how, but it is just a question I'd like to propose, okay? Third, how does particle interaction in confined systems influence the behavior? And I think you're starting to see this because we saw some talks today where people are they're going beyond first, usually it was just one particle systems, but now people are going on to more particles, okay? Please, Ernesto, I don't have much time. Okay. Can particle interaction be used as a resource in quantum control? Again, I don't have the answer, I'm just asking, okay? 5, can the Heisenberg uncertainty principle be used as a resource to design devices? And this is something I'd just like to get in, and this is related to my question 6. What are the physical arguments behind the entropy sum moving away or moving toward the bound? We've seen that a lot. A lot of these entropy sums, and remember, just write, okay, sure, if you want to go into phase space, you can use, like Elvira did, the Weyl entropy, and you can try to get maybe a more exact definition, or you can stay with the entropy sum. But we've seen a lot of very interesting behavior where you're transitioning from one kind of behavior to the other. This is what we're seeing in the confined systems community. And I think it's not enough just to say, well, we have the Heisenberg bound, and it's okay if we're above it. I don't think the entropy sum is used to its full extent if you just use it to say, try to justify, okay, well, because my functions obey the Heisenberg uncertainty principle, then they're good functions and it shows you that the calculations are good. No, no. I think they're actual physical. We'd like to understand what are the physical what physically is happening to the system when the system moves away from the bound or when it moves towards the bound. What is happening? This is something I put out to you. I don't know what the answer is as yet. I hope I'll be able to understand a little bit in the future, but this is something I'd really like to understand. What is happening to the system? Okay, what can we say about the system? Please, Ernesto. Okay, higher order correlations. Okay, I've only got a minute. Saul gave a very, very, very nice talk about it yesterday. Okay, these are just correlations that exist among not just two, but we're going 3 if you want. Saul was talking about 4 more. Okay, what do higher order correlations tell us about interactions in quantum systems? Because if you go, there are a lot of theories that are built up in physics about emergent order. Okay, about an emergent order is due to the interactions. How to measure these interactions? Not just interactions happening at the pairwise level, but interactions happening at the third. Now, it'd be very surprising that there are not too many out there. See, this is one that we have. Saul spoke about it yesterday. Interaction information. 3, when it's a measure of what is happening when 3, the mutual interaction between 3. Okay, very, very quickly. This has been studied. This is studied, and it's very interesting for the people who studied neural activity, neural behavior, because they want to understand. This goes you back now. We're going to data science. We're getting into AI, and we're talking about neural net. We want to understand how neurons interact. So this is an idea of how 3. And then you don't have to stop at 3. You can go 4, 5, but these aren't done as yet. So we want to get some ideas. Saul had an idea of solving these equations yesterday of how you can go about it. Okay, please, Ernesto. See? So challenges, very, very rapidly. I think I have 1 minute, please. Calculation of pair entropies and mutual information in molecular systems. Now, this requires numerical integration. Manuel had a very nice talk speaking about what are the numerical integration schemes and how you could do it. Because really what has been done, the group at Granada, okay, I think it was Juan Carlos and Sheila, they have done atoms. They've studied this mutual information and pair entropies, how they behave in neutral atoms, but we don't know as yet what is going to happen in molecules. Okay? So this is an idea. I think Manuel and Julio in Puebla, they're working on that, and Saul will be working with them too. So they're working on numerical integration measures so we can calculate these things. Okay? Entropy sums, mutual information sums. What are the physical interpretations? Yes, statistical correlations, but can there be? Are these things? How are they interpreted in terms of what is going on in the system? Higher order measures. Okay, and if we want to calculate Wigner function entropies, if we want to calculate Husimi function entropy for chemical systems, well, you can't begin there. What you have to do is you got to calculate the Husimi function, no? Okay, or Wigner functions. And this, this has been, we haven't seen anything recently. Dahl and Springborg, they did some work on this, but if you wanted to go that way, then you'd have to be able to calculate these things in chemical systems. Okay, time-dependent phenomena measures. That is something that hasn't been, well, we've seen some of it, and we see time-dependent systems are being studied more and more, and we've seen some of it during the 4 days. Okay, and that, please, next slide. And thank you very much for your attention. I just acknowledge the work Saul, Humberto, Manuel, Julio, okay, Rodolfo, right? Alejandro, right? I hope I shouldn't have done this because now if I miss someone, then I'll feel very badly. So, okay, thank you very much.
Okay, thank you so much for your talk, Professor Robin. And as a little reminder, please don't hesitate to put your comments or questions in the WhatsApp. And we are ready for the final event, for the final part of this symposium. Yes or not? Yes? Okay. We are ready. Okay, so as a final part of this event, we have a round table with our scientific personalities.
Okay.
Okay, just three? Ah, Roberto
Roberto,
is
yeah.
in Zoom. Okay. Okay, so just to, I have the names here. Okay, in this round table we have the honor to have four professors of WAMI. Yes, from four different areas of science. We have Dr. Rodolfo Esquivel, Olea, from chemistry department. Claps. We have Dr. Robin Sagar, also from chemistry department, as a moderator of this roundtable. Please. And we have the honor to have here Dr. Adrián Mauricio Escobar Granados from physics department. And in Zoom we have Dr. Roberto Quezada Batalla from mathematics department. Okay, so the microphone is yours, moderator.
Okay. Okay. Thank you, Ernesto. Thank you.
Ah, yes, you have another microphone. Yeah, great.
I can
Yeah,
you can pass.
It's on. Yeah,
Okay.
it's working.
Okay. Okay. So, I think we'd like to discuss. Maybe we should remind everyone is that I think it was very fortunate for us planning this event that it coincided with the announcement of our division, in that there's a new postgraduate program that is being offered to the students, which is quantum technologies. So I think it was very we had a lot of fortune in that the timing, it was right timing, you know. So why I'm saying that is that I'd like to just everybody could just to hold that in mind. So what I'd like to do is start off the discussion with the first question, and which I'd like to direct to the professors that are here, is that should this event or a similar one be repeated in the future? What are your thoughts about that? With what frequency? And then maybe also another additional something to think about was that if in what time? What I mean by that is during the term, or during when there are no classes, or how you feel about that. So maybe I'd like to invite Rodolfo to, if you could please give us his thoughts about
Sure.
that.
Thank you very much, Robin. Well, first of all, I would like to thank all the guests and participants of the event, because I believe firmly that this event was very successful, and it was very fortunate also that Robin, in his last presentation, this presentation that we just witnessed, well, he made a very nice recount, a very nice review of what happened in this. I don't know if you have prepared that, but it was something very nice, right? So it is very fortunate that we have this kind of events, and I'm very convinced that we should keep it and take advantage of the momentum that we have gained so far to keep organizing this kind of events. Now the problem is if we should do it the way we did it, I mean, with the effort of the quantum chemistry group, or we should involve the other departments, which should be the most convenient way to do it. But that implies some troubles, I would say, because we know that this area of research is rapidly growing, and it's very easy to think that some of the part of this science, I mean, quantum technologies, could let's say overshine the rest of the science that we could discuss in events like this. So we have to keep how to say that, take care of that balance, right? I mean, how to say that, which emphasis are we going to put in such events? But on the other hand, it would be nice that every department could participate in organizing this event, I would say in a biennial format, not yearly, because it's difficult. I mean, for us organizing this, and I take advantage of my speaking to recognize Roberto Laguna, Saul, Salazar, and of course Robin Sagar for the organizing of this very beautiful event. But it's difficult, right? So I don't know if we keep it every year, but I would say that it's much better to do it in a 2-year format. And the other option that I'm thinking of is that every department could take responsibility for the organizing of the event with perhaps its own imprint in a format that they choose, but with the commitment of the other departments to participate, right? Inviting, I don't know, speakers, but mostly to invite and get involved students. Right. For me, it's the most important part for these kind of events, right? The students, for us, at least in Mexico, is we are, in my thinking, is we are a little bit behind the schedule in terms of research and also in terms of education of this kind of science. I think in other in universities abroad, this kind of graduate students programs, they have been involved in these topics like quantum sciences and quantum technologies. I think a decade ago, easily, right? So I think it is our obligation not to let this thing loose and try to organize this event every 2 years, but get students very interested in these events. That's my opinion.
Thank you very much, Rodolfo. Now, maybe Adrián?
Sure.
Sí, Adrián, your thoughts?
Okay. So first of all, I want to thank again the organizers. This is an enormous work to organize this event. And the short answer is definitely. We should continue with this kind of event because at the heart of the science is just to express ideas. And for example, if I, after listening the talk by Robin, I think it's a pity that the students are not here. Otherwise, I'm pretty sure many of them would be not only interested, but really involved in this research. So definitely the event should continue. About the time, I'm not sure, maybe 1 year it's also a good option, and to include like short courses for students, introductory courses, maybe not only just presentations, no? It may help. And of course, participation of other departments, not only physics, but we have mathematics. But yes, I agree we should collaborate more. And the point is, this growing field requires participation and also a lot of collaboration between different fields. And since this is what is coming in the next years, UAM should not be away from these goals we have in science. So to conclude, I hope this event will take place maybe in 1 year. We can start to organize some different kind of presentation, etc. But we have to start, and it was already done. So again, my congratulations to Saul, also of course to other participants, and let's hope for the good evolution of this event.
Thank you, Adrián. So now we would ask Roberto. Roberto is in online. Roberto?
Yes, I'm here. Can you hear me?
Yes, we can. We can. Please go ahead.
Thank you. Well, first of all, I thank the organizers and also congratulate them for this successful meeting. And in concerning the organization of meetings like this, I think we have to be to think carefully, because you see, we are starting the collaboration between different groups in different departments, and each group has its own dynamics. For instance, our group mathematics has seminars, has conferences abroad and in Mexico. And moreover, you know very well that the teaching duties are very demanding in our institution, in our university. So sure, this is important to organize, to continue the organization of these sort of meetings, but we have to think carefully about the periodicity. Maybe 1 each 2 years could be good. Meanwhile, we need to organize another kind of activities. For instance, a joint seminar, at least during one semester each year, in order to promote the collaboration between the groups. For instance, we could organize a joint seminar during the spring trimester, weekly, with the participation of people from from all departments in the division. I think this will be a good idea to continue the knowledge of between the groups, because we have to promote the collaboration, but the first step is to know what is the work of each group. For instance, for me, it was very interesting this meeting, because I was informed about the research lines of the people in chemistry, physics, but difficult to say if I can collaborate with some of them at this moment. Anyway, I'm very interested in searching for this collaboration, and I think that a seminar like the one I'm proposing could help to know better and find the opportunities to collaborate.
Okay. Thank you, Roberto. And it's very interesting what your last comments, because this leads into the next question. I'd like to ask what further actions can be taken to stimulate collaborations between the different departments in the division. And I think Roberto was speaking a little bit about this. So I'll just hand it over to Rodolfo
Thank you.
Hear his thoughts.
Yeah, I agree very much with Roberto's proposition. I think we should organize more than a seminar. I could say it's something like a workshop, a yearly workshop. But when the distinction would be that the students get involved. I mean, I would try to get the students involved in the organization. I mean, they won't do anything, but I mean the whole thing. But we can help the professors to try to establish some kind of program, but with the aid of the students. That, for me, that's the central plan of a yearly event. And of course, courses will be very important to continue with this idea of having this divisional effort that we are undertaking with the graduate studies program. So that was a very important step towards this end. So I think I will go for a yearly event as a way of a workshop.
Okay, thank you, Rodolfo. Adrian?
Yes, pretty much I agree with Rodolfo. A workshop it's perfect for everyone, for students, but also for professors, and to let the students that this is not like a fancy subject. Actually, this will be in few years the, I would say, the general culture about science. I mean, in physics and mathematics, and also in chemistry. So this workshop will really help to fulfill this goal. Another step we can take, we already between different people, we start to talk about some collaborations, either like co-advisors of common students, or even directly doing research, right? So this is a step I think will really enforce the goal of this event. Of course, it takes more than months, but maybe 1-2 years to see if it's success or not. But even if for sometimes it will not be easy for mathematicians maybe to directly collaborate with physicists or with chemistry. I think there is a lot of opportunities, in particular physics and chemistry. We have a lot in common, and also students. So probably this will be easier, and just more maybe to promote more the event, and during, of course, classes, because it's difficult maybe for students to attend during the, for example, this week, but that can be easily arranged. Thank you.
Thank you, Adrian. Roberto, do you have anything further? It was you
Yeah,
brought up the idea, so please go ahead. Go ahead.
Yes, I think I like. I think this on a school workshop would be a good, a precious idea, a beautiful idea. Just to once a year it will be very nice. School workshop. Think about the students and try. We both try to involve them. So for them, courses could be very interesting, and also talks. But of course, talks are more for researchers than for students. And school workshop, the format of a school workshop could be a very nice idea.
Okay, thank you, Roberto. Now, just for people who are outside of the UAM, our division, we're organized here in the division, but one characteristic which is it doesn't happen in everywhere else, is that natural sciences in our division, we are incorporated with the engineering departments. So as a consequence of this, it's very important that we have a voice from these engineering departments. So the next question is, what actions are needed, if any, or how are we going to incorporate the engineering departments into future events? So please, Rodolfo, I can.
Thank you very much, Robbie. Yeah, just to summarize a little bit of what I said before. I think if we can organize a bi-yearly meeting, international meeting, with the shared commitment of the departments to co-organize these events, it would be nice that every time the event is organized, every department can imprint, right, their own interest. Because my fear is that, quantum technologies are very, how to say that, impactful. So the quantum sciences, that in this case, that was the idea of this event, we gather everything together. But if we think in a departmental organization, it could be for a different direction. It could go to a different direction, which is good. Every 2 years could be organized with a different direction, but with the commitment of all departments to participate, with, of course, students, researchers. And the other idea was to organize this yearly event, the workshop, with students, right? With the mm, where the students will be the central part of the organizing committee, let's say so. And of course, there will be courses. We have undertaken this project of the incorporate new courses into the graduate students program in two directions: quantum sciences and also quantum technologies. That's the other step that is helping us. So we are taking steps towards the end of not losing this effort that we have initiated right now. So I will go with these two ideas, and I think that the engineering departments can participate if they wish, of course.
Okay, thank you, Rodolfo. Now I'll pass it to Adrián, please.
Yes, so no, definitely if more people in different fields can join the event, it will help for the quality, but also to expand the scientific horizon. However, probably at this very first step, already 3-4 departments, it's a huge challenge to get involved. But let's see, I would say that the first thing is to see what our colleagues in those departments are doing related with quantum technology. As far as I understand, the experimental part is not somehow easy and not well developed actually in our country. But yes, if there is some efforts, if they can present specific, I don't know, devices, that will be helpful. If not, maybe they can explain to us, which we are not experimentalists, how other people in the world are doing these experiments, and that can help. And as Rodolfo said, well, it depends if they want to to participate. I'm sure they want. So let's invite them and talk to them to get more collaboration from them. Yeah.
Okay. Thank you, Adrián. And Roberto, please go ahead.
Well, yes, I have not a clear idea of how to involve engineers, but I think we must involve, we must ask them and talk with them and try to understand their necessities, no? And we will, talking with them, I think we will understand better how to involve in this project. This is my opinion. We have to take their opinion. We have to ask their opinion.
Okay, thank you, Roberto. And now, a personal question for each of the panel members. In your opinion, in personal opinion, has the event provided new perspectives or potential collaborations? Please, Rodolfo.
Thanks, Robin. I think that's a very difficult question to answer, but I guess that well, in the future we'll know, right? I mean, established collaborations will continue. This is a proven of that, right? We have seen many collaborations throughout many years, and they will continue for sure. But new collaborations require time. We will see, right? We are paving fertile soil, I think, for doing that. But we have to continue this effort. I think that we have recognized ourselves that we are working in this field. I mean, not only us in quantum chemistry group, but also in the other departments, right? There are many people working in these things. So let's get together and do something for the future, right?
Thank you, Rodolfo. Now, I'll pass it over to Adrián, por favor.
No, in my case, it's not difficult. Actually, it's in my personal opinion. At least during these years, I got some 3-4 clear ideas what can be done, not only by students but also with collaborators. So it was really helpful for me to listen all this knowledge, and since UAM already has a very well established history in particular information theory, we have to take advantage of that. No? You already have collaborators outside Mexico and many students, so let's increase this already group. This is my opinion. Don't try to invent new things. We know how it works. So let's enforce this very nice work that we saw during all the week. So this is my personal opinion.
Okay, thank you, Adrián. Roberto, please, go ahead.
Well, after this symposium, my impression is that the field of quantum technologies and quantum information sciences is a huge topic. There is a lot of lines, but anyway, we are ready to try to collaborate with physicists or people from chemistry, but you see, we have a special deformation because of the mathematics. Anyway, we will try. We are trying to understand and to find the common language and the common problems to work on. So we are ready and we have we look for opportunities to work with colleagues from physics and chemists.
Okay, thank you, Roberto. And we just like to point out the organizers, on behalf of the organizers. We are so grateful. Arturo is the divisional technician who is responsible for the transmission in YouTube, and he was here from day one, and he accompanied us all the way through, and we're so grateful for him because it went off without a hitch, no problems. So Arturo, if you are seeing this, thank you, thank you. Yeah. So one other thing, everybody is free to have an opinion on these things that we're discussing here. You can use the WhatsApp chat if you would like. If you have an opinion, you would like to express an opinion, please do write us and let us know what you feel about this. Okay?
Opinions and suggestions.
Opinions and suggestions. Thank you. Okay. So one thing also. So we were at the end of the event, but one thing, we're at the end, but really not quite at the end, because I would just like to remind everybody that there is an issue in Revista Mexicana de Física that we are planning. So all the participants, we're asking you have until March 2nd, okay? So we're going to be publishing the proceedings of the conference. The information is detailed in previous emails, but I think we are going to be in contact again with you with more information. So please keep this on your calendar. It's between 4 and 8 pages LaTeX output. The LaTeX template it's all described in the emails that the organizers have sent out. But please do try to submit a work so that we can have a history of this. Okay. Wonderful. So okay. So anything. So we close the session, and thank you, Rodolfo. Thank you, Adrián. Thank you, Roberto. Thank you very much.
Thank you. Bye.
Sí, estamos transmitiendo.
Apaga, descarga el cable.